So what is the idea? So the idea is I have the equations of motion. I have the torques which are coming from the controller, voltage or torque. So what we will do is we will assume that the torque is related to, is of this form. Okay. So the motor torques are related to some alpha times tau prime plus beta. So, and what is tau prime? Tau prime is nothing but the PID controller. Okay, so tau prime is what we compute using the PID or PD controller. I am going to multiply that part of the PD controller torque with some alpha and add it with some beta. So this is the basic idea. So I am going to scale up that PD torque which is coming from the PD controller and add it to this. If we use alpha as mass matrix and beta as this, if I know this thing exactly, then the equations of motion become this. Okay? So as I said, tau prime is nothing but the PD controller, and then the error equation becomes like this. So let's look at what is this. This is the important diagram. So I have this robot. There's a torque which is coming, okay, from the voltage which is input to the robot. We are measuring Q and Q dot. So this voltage is proportional to one part which is PD control, same as the equation of the PD control, exactly same, you can go and see it. But it is multiplied by this mass matrix, and you are adding this Coriolis term, gravity term and friction term. So this dotted block here comes from the equations of motion. This dotted block comes from the PD controller. Okay, so this is the basic equation, most important equation. So we have PD control, which I already know what I am doing. I'll multiply by some mass matrix, which is M, and I'll add this. So if you were to do this, then you can see that the effective equation is a linear equation. Okay, so tau prime is equal to Q double dot. Okay, and the error equation is a simple linear decoupled error equation, which is why I said in the computed torque scheme, ideally, if everything cancels out, I know the model exactly, I will get a linear error equation. And now, if you have a linear error equation, I can choose Kp and Kv. So this is like x double dot plus 2 psi omega n x dot plus omega n square x. Okay, so I can choose Kp and Kv to give whatever psi I want and whatever natural frequency I want. Okay, and it will be same everywhere in the workspace because there is nothing else here. This equation is telling me there is no theta dependence. Okay, it does not depend whether the robot is like this or the robot is like this. Okay, so ideal conditions, when everything is known exactly, the error equation looks like this. Okay, and this is the implementation of this model-based controller. So I have one part which is based on the Coriolis term, the gravity term, whatever is the assumed friction term. I have the mass matrix. Some part here is related to the existing PD controller which I have already designed, which does something. Okay, and then I have scaled that value, added, multiplied by m of q, and then I have added to that all the other nonlinear terms. So in some sense, what you are saying is, I know there are nonlinear terms in the equations of motion. I know the robot is nonlinear, but if I know what those terms are exactly from the dynamic equations of motion, I can use it to cancel them. Okay, so effectively I am cancelling out all the nonlinearities and making it into a linear system. So together all of these things, okay, the effective equation looks like this. Okay, after all this cancellation, after using all this dynamic model, the effective error, so error is theta d minus theta. Okay, so theta d is the desired joint, theta is the measured joint, and this is a simple second order equation, and I can make it overdamped, I can make it underdamped, I can make it critically damped, whatever I want. Okay. So this is the basic idea. It's a very powerful idea. Many people have used this both in research, as lots of papers have been written in many places. Now they are slowly being implemented in actual robots. Okay. So it's a very, very strong, powerful idea which is now being used. Okay. What happens if it is not known exactly? As I told you, that we need to use the model. So if I do not know the mass matrix exactly, so suppose this is the actual mass matrix and this is an estimate of the mass matrix. Okay, so some error is there. So maybe the load is not exactly 5 kg which I have picked up, it is 4.9 kg. Okay, so then it is not exactly known. So if you know some estimate of the mass matrix, some estimate of the Coriolis term, some estimate of the gravity term, and if you still use it, what you can see is the right hand side is not 0. If it was exactly cancelling, the right hand side will be 0. But here, if they are small, the right hand side is a small number. Okay, the disturbance which is happening on the right hand side is a small number. Okay, and this is the reason why I said the better you know the model, the right hand side which is making all the complications, there that is a small number. Okay, and hence better model, use it, get better performance. Okay, you can, these are all mathematically derived. Yeah, tell me.
So this what you showed right now is a model that can work on an industrial robot indoors.
Huh?
It is something that works very well indoors. Suppose you were supposed to put it on a mobile robot arm which is outdoors and there are other effects like wind, etc. Where in the model would you add those?
Yeah. So if you, so that is dynamics, no? So so this is the assumed equation of motion of the robot. Okay, so it is related to theta double dot, Coriolis term, gravity term, and this. If you have other effects, you have to add it here. Okay, so I'm sorry, I need to go. So you can take a look at this, but let me just show you one actual experimental result. Okay, so everything boils down to, I can keep on talking for hours on theory and models and so on, but eventually you have to show that it works. You have to do experiments, you have to go to some company and say that, oh, this is my new controller, try it and show that it works. Okay, so this is exactly what we did. So there was this two ME students many years back, they went to BART. So BART had this robot, it's a 5 degree of freedom robot, which, so there is one motor here, one motor here, one motor here, and two more motors here. Okay. So again, they were running a simple PID controller scheme, PD controller scheme. So we said that we will implement a computer talk scheme on that. Okay. So I am going to show you some results. So this is what happens. So this is the desired trajectory. So the robot theta 1 has to go from 0 to some 30 degrees and come back to 0 degrees. So this is the path. It's a nice, smooth, cubic trajectory. So the existing PD controller, which is what it was, is this thin dotted line. Okay, and this is the model-based controller which is implemented. So fortunately they had a CAD model, because BART makes their own robot. They have a CAD model of the robot. They know what mass, length, everything is known. So instead of this, suppose you plot the error between the desired and the PD controller and error in the model-based controller. So what you can see is the error in PD control is like 2 degrees or 4 degrees along this path. Okay, is that a lot? Yes. Okay, so you can't have a robot which is deviating. I want to be at 32 degrees. It is going plus minus 2 degrees. It's quite a bit. Okay. Just by implementing the PD control, we brought it down to less than a degree. So this is the plot of the error using PD control. Okay. So hardware remains same, All we have done is change the software or change the controller. Nothing else has been changed. It is not as if you are using a better motor or the gearbox has been changed so there is less backlash. All those, nothing, they won't let you touch it. All they will say is, here is the computer, you can change the program. Okay? So it has come down by so much. You can also see for the second joint, the error was initially like 2.5 degrees, now it is about 1 or 1.5 degrees. So just by changing the program, just by using the model-based terms, just by using the equations of motion, we reduce the error by half, approximately. Okay. You can also see something more interesting. As you go further and further out, so this is for the second joint. Third joint, you can see that the error is reduction is much smaller. Why? For the fourth and fifth joint, I am not going to show you the plot, there is no reduction. Okay? And the reason is, as you go outwards, so the fourth joint is here, the fifth joint is here, very little dynamics is there. Okay? The first joint sees the entire robot arm. The first joint sees all the dynamics of all this changing inertia and so on. The last joint, nothing is being seen. Okay? So, if you have dynamics, then use it. If the dynamics is not very important, doesn't matter. Okay, whether you use PD control or model-based control. Okay, so I'm going to end here. I completely skip the simulation because we need to go. If you have any question, you can always ask me, send me email, I will reply. But the full notes are there with you. Okay. More details are there in my book. So I have to advertise my book. So those of you who want to buy my book, it is available in many places, including Flipkart and various other places. So the book contains much more details. Okay. So please buy it. If you find mistakes, let me know. Okay. So it has been around for a while. Many of the mistakes have been corrected, but if you still find some mistake, please let me know. Okay, so summary, multi-link robot, serial robot is a nonlinear system. Okay, linear PD control does not give very good performance. It works. Okay, it does not give uniform performance everywhere. And if you do this computed torque, model-based control, there are various names. It is also called control law partitioning. Why? Because one part of the control law comes from the PD control, one part of the control law comes from the model. Okay, there is another term which is called control law partitioning. If you have ideal equations of motion, if you have ideal computed torque, you will get exactly same uniform performance everywhere in the workspace. Okay, otherwise you get whatever you have. It is based on how much you know. Okay. And you can show that it is always superior to PD control, PID control. It is always superior, both simulation and experiment. I did not show the simulation results. Okay. So I'm going to stop here. So this is the end of this thing. We have exactly 5 more minutes before we leave. So if you have any quick questions, I can answer. So, those of you who are interested, you can write to me, but full detail is here. I did not show the simulation because, simulation means what? Who knows what program I have written and what plot I am showing you. Okay, but it is very hard to, this is more believable, no? Right? I mean, how easy do you think it is to generate a plot like this? It is not very easy. Okay, so you can't fool anyone. So that's why experiments are very important. Okay, it is very hard to show some plot like this. This is a true actual experimental result. Okay.
What was the nature of the load?
Huh?
What was the nature of the load in this experiment?
This robot was moving some 1 kg or something like that at the end. This is a robot which was designed by Barr to pick radioactive samples from somewhere and put it somewhere else. Okay. Thank you very much, and sorry for this last quick thing. Anybody interested, you can send me email.